The next speaker is Dr. Ashwin S. from Geetam University, Bangalore. The title of his talk is Rouse Polymer in Random Media, Some Exact Results.
Good morning and thank you for this opportunity. My talk is going to be on how to diagonalize a certain class of tridiagonal random matrices which have Toeplitz feature in them. So these kind of matrices, Toeplitz matrices are basically constant diagonal matrices, and here we have segmented constant diagonal matrices, and these elements of each of these segments come from a random distribution. So I call these kind of matrices tridiagonal randomly segmented quasi-Toeplitz matrices. So the motivation for this comes from when I started studying chromatin dynamics, where we try to understand how the chromatin moves inside this very heterogeneous environment, which is filled with phase-separated liquid globules. So the chromatin basically flows through these several phase-separated liquid globules, and the experimentalist I'm collaborating with, he does super resolution microscopy, where he tags these nucleosomes. So basically DNA is bound around certain proteins known as nucleosome. These are the primary packing units of the chromatin. And they light them up with some fluorescent molecule, and they are able to track them for about 1 second or so. So during this 1 second period, typically these nucleosomes move about 150 to 200 nanometers, and these globules are basically about 300 nanometers. With respect to those time scales, the randomness is basically quenched. So a popular model for studying chromatin dynamics is the Rouse model, because they have the same kind of MSD exponents as the live chromatin polymer. So I'll very briefly go through this Rouse bead spring polymer. So these are basically beads which are connected with certain spring constants, constant spring constants, and these beads do not have volume penalty when they overlap over each other, and this model can be solved exactly in the overdamped Langevin limit, and this matrix which comes up here, the Xi matrix is basically the damping coefficient matrix for in the case of a Rouse model it is uniform, and this is basically a Toeplitz matrix which can be exactly diagonalized using a Fourier transform. It has a very elegant eigenvalue which is basically sine square of some argument over here. But in the case of the Rouse model through a heterogeneous environment, we have these beads going through different globules of phase-separated globules, and hence experience different damping coefficients which are taken from a distribution, and we have this tridiagonal randomly segmented quasi-Toeplitz matrix. In order to solve these matrices analytically, I will be using something known as Chebyshev polynomials. These are basically certain trigonometric polynomials which follow the same kind of a recurrence relation, but the first term is, for the first kind of Chebyshev polynomial is x, and for the second Chebyshev polynomial is 2 of x, and when these functions are expanded in terms of cos thetas, they are called as the Chebyshev polynomials. So if you take in the simplest case is when you have only one segment of this is exactly a Toeplitz matrix, and we can expand the determinant of this matrix, and you find that this kind of an expansion of determinant on scaling with the Xi to the n1, where n1 is the number of beads in the first number of rows in the number of rows in the first segment over here, we get exactly the Chebyshev polynomial of the second kind. So the eigenvalues now can be is exactly that of the Toeplitz matrix. But now when we go to the second step where we use two segments over here, we can expand, we can do a Leibniz expansion along this boundary, and we find that the determinant can be represented in a very similar fashion as the Toeplitz matrix, but it has a phase factor phi 2 in it, a certain kind of phase factor coming into it. And this phase factor depends on the determinant of the first segment. So the eigenvalues are very similar to the eigenvalues of for the Toeplitz matrix, except that the argument has a phase factor phi. We can actually generalize this, and we have a theorem, and you can see the eigenvalues for any m segments has the same form, but this phase factor phi comes in, and now this phase factor phi depends on two parameters Vm and Um, which can be written as a product of random matrices. The elements of these random matrices are basically random functions which are given by the combination of the Chebyshev polynomials. Very briefly, most of the proof is there in this paper of mine, but I'll very briefly say, I'll give you a very brief outline of the proof. So what we have is, we can now get the eigenvalue simply purely by the process of induction. But the phase factor, we need to do a little more. We need to expand these determinants in terms of the Chebyshev polynomials with certain coefficients, which can be written as a transfer matrix in this form. So we have this kind of a form. And then the Rouse model can be like calculated. So all these results are exact for a given realization of randomness, for a given set of xi p's which you have. In order to go to the continuum limit, where the matrices are very large, we need two or three things. One is we need the distribution of these phi's in the continuum limit. We need the density of the roots. We are given the distribution of the xi's, and we are given the size of distribution of the size of these segments. We assume that this, for the calculation which I do, I assume that it's a Gaussian with a very small width, and then I can, so now my problem is that the density of the roots are easily calculable because we know the form of phi's, but this is a little more complicated. The distribution of the phase is a little more complicated. We will notice that actually this kind of random matrices come up in disordered systems, and it also comes up in the Ising model with defects. There's a classic work by Wu and McCoy in which they basically outline how these can be solved using Furstenberg's theory. So basically what you do is you go to the U and V plane, and then you use this 2 cross 2 random matrix as a propagator as a kind of evolution operator for these coefficients. So if you have lots of segments in this system, what happens is at the end of the day, this distribution gets to a limiting distribution. The phase distribution gets to a limiting distribution. We can then write this kind of a phase distribution as an integral equation, because the more, after a certain amount of multiplication of these matrices, the integral will not, the distribution of the phases will not change. So we can calculate the distribution of the phases, but this has to be done numerically. We have calculated the distribution of the phases for various values, but now that we know the distribution of the phases, we can go back to the distribution of the eigenvalues, and this basically has two forms, the first term and the second term. The distribution of the phases come up in the second term, but interestingly, the second term comes up with the size of the matrix at the denominator. So in the limit of the large random matrix, the second part actually, even though we know the distribution of phi, if we want corrections we can do, but in the large matrix limit, which is we have 3 billion nucleosomes inside the chromatin, this is an exact form. I've calculated these for a few distributions which we have. I've calculated this for the uniform distribution and for the chi-square distribution and for the Toeplitz matrix. The red curves here are the exact values from the theory, and the histograms are from basically diagonalizing things on the computer simulation. And we see very clear, these are the almost accurate maps. So thank you for your attention. If you have any questions, I can.
So in the last slide, what is different in these 4 plots?
Which one?
These 4 plots, what is different?
Oh, the distribution of the x's, the damping coefficients. Here I've used a constant damping coefficient, so you get this Toeplitz distribution. And here I've used the x's, which come from basically from a uniform distribution between 0 and 1, and these are from chi-square distributions. This I use because these can be parameterized to mimic any kind of distribution, several kinds of distributions.
Can you calculate also the joint distribution of the eigenvalues?
Joint distribution of the eigenvalues? I haven't actually thought of that actually. So,
because this is the average density of eigenvalues. What you compute.
Yeah, this is the average distribution of the eigenvalues. Yes. So you want P of lambda 1, lambda 2 and things like that.
Lambda n, exactly.
I have to think about it. Okay. I'll probably think about it.
Any more questions?
So, I mean, since you have a sort of a random tridiagonal matrix, right?
Yes.
So, if you look at the eigenfunctions, I mean, typically one expects that they should be completely localized.
I'm sorry, I can't hear
They
you.
should be localized. I mean, if you look at the
be-
eigenstates.
The eigenstates are localized, you're saying that?
Like if you take a tridiagonal
The
matrix.
eigenvectors or what?
Eigenvectors, yeah.
I've not calculated the distribution of that's my next thing. Like I will be using this eigenvalue eigenvector theorem. You can actually calculate the eigenvectors also.
Yeah, and so there's certainly be
Yeah, you should be.
localized.
Yeah, you should have localization because of
But
that. Because
I mean, I don't know if it will have any effect on the polymer really, because polymers look like because with the overdamped dynamics.
Yeah,
it'll
right.
be
So
interesting
these are
to-
basically these lambdas are basically the inverse relaxation time scales of the Rouse modes. So large lambda would imply short time scales, and a small lambda would imply long time scales. So in that sense, you can infer what kind of localization is there.
Let us thank the speaker.